NASA's Jet Propulsion Laboratory presents the Von Karman Lecture, a series of talks by scientists and engineers who are exploring our planet, our solar system, and all that lies beyond.
Hey, good evening, ladies and gentlemen. How's everyone tonight? Good. Well, thanks for coming out to join us this evening. As humans drive Earth's climate into a new regime, it is critical to keep our fingers on the pulse of the planet. Sea level rise is both a stark reminder of our impact on the climate and its impact on us. The oceans capture over 90% of the heat trapped by greenhouse gases, expanding as they warm. They also collect water from melting glaciers and ice sheets, making sea level rise a doubly important indicator of global warming. Without adaptation, a 2-meter rise would displace 187 million people worldwide. Sea level will continue to rise, but we don't know how fast. Like its predecessors, the Jason-3 mission will serve as our eyes on sea level rise. Measuring global sea level once every 10 days, it will chart out the global rise of the oceans, a rise that is unlikely to subside or reverse for generations. But Jason-3 will be more than a sentinel of climate change, as it will also measure the tilt of the ocean's surface, providing oceanographers with information about ocean currents, measure wind and waves, helping forecasters predict marine weather, and even find local warm spots that can intensify hurricanes. In short, Jason-3 will be pretty cool. Our guest tonight has been at JPL since 2004 and is now the NASA project scientist for the soon-to-be-launched Jason-3 mission. In 2010, he was awarded a Presidential Early Career Award for scientists and engineers by President Obama for his pioneering research on understanding the causes of sea level rise and the ocean's role in a warming climate. Most recently, his project Oceans Melting Greenland, or OMG for short, was selected by NASA as an Earth Ventures mission to study how the oceans are melting the Greenland ice sheet from below. In his spare time, he studies comedy and improvisational theater. Last year, he graduated from the Second City Improv program in Hollywood, where he learned to communicate about climate change through comedy. Despite his love of laughter, though, he has not yet quit his day job. Ladies and gentlemen, please help me welcome tonight's guest and a good friend of mine, Dr. Josh Willis.
Thanks a lot, buddy. Wow, thank you, Mark. That was incredibly erudite and well-written. So I just will end there. See you guys. I really appreciate the warm welcome, and I really appreciate everybody coming out tonight and everybody who's watching us streaming on the interwebs and on NASA TV when it airs tomorrow night. Why am I here? Well, I'm here to tell you about Jason-3, which is the successor to the successor to the successor to the mission that got me my PhD back in graduate school. And that mission was called Topex Poseidon, and it was our very first look at the oceans from space in a way that we could really measure them well enough to tell us something incredibly useful to oceanographers. And I'll talk a little bit more about that as we go along. But I also want to really drive home the theme tonight that this is one of the fundamental ways in which we measure human-caused climate change or global warming. Really, 2/3 of the planet are covered with ocean, and as we look at our changing climate and our changing planet, really we need to be looking to the oceans because that's where the action is. So you guys look like a really nice crowd, so hopefully I'm not going to say anything that will get me beat up later. I ask, because it's happened before. So I am going to say global warming's real, so please don't beat me up. And I want to start off with this slide. I like to start with this slide because it's a reminder of just how big the oceans are. The Pacific Ocean covers about 1/3 of the planet's surface, all by itself. If you were to rotate this globe just a little bit to the east and look at it from this same view, almost the only thing you would see is the Pacific Ocean. The oceans cover 2/3 of our planet's surface, and they play an incredibly important role in our overall changing climate. So in this sense, you might not be surprised that it's an ocean mission that's really measuring the most fundamental aspect of climate change. So as Mark kind of set up a little bit here, this is the actual fourth mission in a long line of missions that have measured sea level from space. Starting with Topex Poseidon, which was launched in 1992, Jason-1 in 2001, and this graphic's a little old. Actually, we lost Jason-1 just a little under 2 years ago. And Jason-2, which is still in operation, and of course Jason-3, which we hope to launch this summer if all goes well. So why do we need to keep measuring the oceans like this? Well, if we take a look at how Jason works, just to give you kind of a fundamental idea of what's going on with this satellite, it looks something like this. In a sense, it's one of the simplest measurements we can make from space. It doesn't require a whole lot of interpretation or guesswork to kind of figure out what it is you're really measuring. All you do is you bounce a radar wave off the surface of the ocean from your satellite. So we shoot a radar wave down, it comes back up. It travels through the atmosphere and the ionosphere and some other things, and we have to do some corrections in order to understand this real distance. But essentially, we're just measuring how long it takes for this wave of electromagnetic energy, essentially a radio wave, to go down to the surface of the Earth and come back up. And that tells us the distance between the satellite and the surface of the ocean. So if we know where the satellite is, then we can figure out how tall the ocean is. And essentially, this mission flies about 800 miles out in space, and it can measure the accuracy of about a 10-kilometer square on the ocean. It can measure the sea level with an accuracy of about 1 inch from 800 miles up. So it's really an amazing piece of engineering and an amazing technological feat. And when you do this once every second, really, for 10 days, you cover the entire surface of the Earth's oceans, or almost the entire surface, once every 10 days, you can see not only changes in the ocean that have to do with changes in ocean currents, but you can also see the increasing volume of the ocean as a whole. So this is the way in which it really is one of the most fundamental tools for measuring climate change. So just to give you an idea, we keep talking about ocean currents, and essentially whenever a large current happens in the ocean and it persists for several days or weeks, then it literally tilts the surface of the ocean. And we can measure that tilt with this satellite, and we can figure out what the currents are and how they're changing especially. But when you average over the whole planet, you really see this other signal, which I'll talk more about as we go along. Now, the measurement of ocean currents has all kinds of important uses. And in April of 2010, there was an explosion aboard the Deepwater Horizon oil rig in the Gulf of Mexico. 11 people were killed during the eventual sinking of this platform, and many others were injured. And eventually, the platform was lost completely, and the well it had been drilling began to spew oil into the Gulf of Mexico. And it was because of satellites like the Jason missions that we were really able to understand and predict the currents that would carry this oil around in the Gulf Stream, eventually mixing it up and dispersing it. Some of it eventually probably even left the Gulf through the Gulf Stream, which runs around the southern tip of Florida and heads out into the Atlantic Ocean. So this is really an incredibly powerful tool for understanding ocean currents. And the Jason mission, both 1 and 2 were in operation at this time, and another satellite which measures sea surface height but in a slightly different way. Envisat was also used to map this oil slick. So measuring the ocean currents from space has long been important to people like the Navy and other users of data that tells you how the currents are moving in the ocean, fishermen as well. Another thing that measuring how tall the ocean tells you is how warm the water is. And this is a really fundamental piece of how the oceans change. Warm water literally expands. So a blob of warm water in the ocean stands taller than a blob of cold water. And this is incredibly important for things like hurricanes, which suck their energy out of the ocean in order to survive. So these massive storms are skating over the surface of the ocean, sucking up heat out of it and putting it into the atmosphere. And as they do, they mix up the ocean. But what's really amazing about the satellite altimetry is it tells you not just that the ocean's warm right at the surface, but that it's warm over depth too. And so this is a plot showing the path of Hurricane Katrina, where essentially the hurricane was fairly small as it had passed over the southern tip of Florida, entered the Gulf, and as it started to turn north, it hit this huge blob of warm water that was a giant eddy. And this pool of warm water fueled it into the Category 4 and eventually 5 hurricane, which sped up and eventually made landfall very close to New Orleans, as you all know, with disastrous results. But if you only looked at the surface temperature of the oceans, you wouldn't have been able to tell why the hurricane sped up right as it went across this big blob of warm water. So it turns out that satellite altimeters also tell us about hurricanes and how and where they might speed up due to the presence of extra warm water that's really hidden down beneath the surface. Another trick that we can do with our altimeter data, I said at the beginning that this is a follow-on mission to a series of satellites that's been flying since the early 90s. So we now have over 20 years of an incredibly accurate record of how the sea levels have changed all around the world. And what's interesting is that we're slowly now starting to be able to tease out the part of sea level change, local sea level change, that's caused by human-caused climate change from the kind of natural fluctuations that happen in the ocean. Now, if we look at the ocean as a whole, if we average over the entire planet, it's easy to see the human-caused component, the long-term trend of global warming. But if you look locally, it can be swamped for a period of 20 years or so. As a matter of fact, on our coast right here in Southern California, we've had almost zero sea level rise for the last 20 years. That's despite the fact that the entire planet has seen a couple inches of sea level rise. So where did our sea level rise go? Well, it turns out it went into the western Pacific Ocean due to a sort of natural cycle, which we call the Pacific Decadal Oscillation. And finally, now that we have this 20-year record of how the ocean levels are changing, we can begin to tease apart the natural cycle, which looks something like this, from the part that's caused by that's really driven by human-caused climate change. So this is a very recent study, which was really exciting because it was the first one to really say, look, some of this warming in the Western Pacific, which we used to think was just a natural cycle and would eventually cool back down, may be kind of permanent. It may stick around. And if we look in our climate models, we see very similar patterns to where these things are warming. So this altimeter data is really helping us tease apart the human-caused changes in our oceans from the kind of natural cycles that have always been there and will continue to be there. So it's really an incredibly powerful data set. And there's one last quick result I want to show you that's sort of new and fun. I've been working with my colleague, Veronica Neves, to look at the recent global warming hiatus, as it's been called. Now, you may have heard something about this in the news. Scientists have been kind of puzzling over what's going on with global warming in the last 10 or 20 years. And it turns out that's actually a misnomer. You shouldn't really be calling it the global warming hiatus, because if we look at the surface temperature in the last 20 years, it was rising pretty fast in the 80s and 90s. And then in the last decade, global surface temperature kind of flattened out. And we didn't have a very fast rise in global surface temperature. And it turns out if you look at the different places in the ocean that are either warming or cooling, in the Pacific Ocean, right at the surface, we've had this enormous cooling. So, what's going on? This cooling was big enough to kind of hide the increase in global surface temperature for the last 10 years. But as I probably already mentioned, or as we'll get to in a little bit, global warming didn't really stop. The surface temperature stopped increasing, but the warming as a whole continued. And it turns out that even though there wasn't much warming at the surface, there was a lot of warming going on just below the surface in the Pacific. So a lot of this heat was hiding in what we call the Pacific warm pool. So really, there is no hiatus in global warming. There was a bit of a hiatus in surface temperature, but in terms of global warming, we're still chugging right along, as you'll see in some slides a little bit later. So, I want to talk about global warming, but you can't really talk about global warming without talking about the weather a little bit. And it's important to remember that the weather is different than climate. So, right now we're having a heat wave. It's hot. I got in my car on the lab this afternoon, and the little thermometer read 91 degrees. So it's been a heat wave. We've had a little mini heat wave here in California. And of course, on the East Coast, they're getting blasted with huge snowstorms. But you got to remember that not everything is related to global warming. We get these warm spells and cold spells, and they come and go. And this is just part of the natural weather that we've had for decades, for millennia. So, sometimes we try and we go, oh, wait, tonight's lecture is canceled on global warming because we're snowed out, right? So global warming must not be real. But hold on, you got to remember, this is really a weather phenomenon. It's not a climate phenomenon. This is something that comes and goes in the matter of a week or two, and it can take us on an awful wild ride. But it's really not human-caused climate change, and it's important to keep that in mind. The climate you could define as the long-term usual weather conditions of an area, a country, or a planet. So you have to keep in mind that climate is something that changes over the course of decades or a century, but not 2 weeks. That's not climate change. But what is climate change? When I talk about global warming, we often look at this curve. This is the temperature curve for the last 120 or 30 years. And it's the surface temperature. This is, again, how the surface temperature has changed. And you can see right at the end of this, this is not totally up to date, but right at the end, here's our hiatus, right? This tiny little flat plateau. But what's global warming? Well, global warming is this 1.5 degrees Fahrenheit of increase that we've seen over the last 100 years. And that's actually not stopping. If we look at climate change and global warming in kind of the context of the last 10,000 years, it really brings to light why this is such an important issue, and one we can't really afford to just ignore or blow off. For the last 10,000 years, human beings have enjoyed a very stable climate. Prior to this, people were more or less evolved into what they are today, but we were nomadic. We would not settle in single places, and farming was not really developed until the climate stabilized about 10,000 years ago. And it stabilized into this relatively warm climate. Now, that's not to say nothing was going on in terms of climate. You guys might have heard about the Little Ice Age. The Little Ice Age followed what was called the medieval warm period, which was a little warm period right here. This is surface temperature over the last 20,000 years. And the scale gets a little finer as you go to the right. But 20,000 years ago, we were in the middle of an enormous ice age. And this was a period of time when glaciers covered much of North America. Chicago was buried under 2 miles of ice. The Great Lakes were being formed. And it was an incredibly different climate. And human beings didn't really settle down and begin to develop farming techniques and eventually cities and states and technology and iPhones, right? We didn't get iPhones until 10,000 years of a stable climate. So if we look out into the future, this was the change out of the last ice age into the stable period. It's about 5 degrees Celsius in the global average. And what we're looking at in the next 100 years, relatively short time period compared to the last 10,000, in the next 100 years, we're looking at something between 2 and 5 degrees Celsius of warming. So this is a major change in our climate. We're looking at an incredibly different planet compared to the one we've had and enjoyed for 10,000 years, the one we've built our civilization on. So it's a pretty major change. Now, I'm not saying it's the end of the world, but it's definitely something we're going to have to deal with. So what do you think causes climate change? This is the interactive portion, so feel free to just yell it out. CO2, somebody said. Some would say Democrats. It's not Al Gore's fault, Not everybody loves Al, but it's not his fault that we're heating up the planet. He was really just the messenger, or one of them. But what really causes climate change, you guys got it. It's CO2. If we look back over the last 100,000 years of the planet's history, we see these rises and falls in CO2. And these actually track the rises and falls in the temperature of the planet. And these cycles of sort of 10,000 years of warming and 100,000 years of cooling go back for millions of years. And what had happened was, we talked about 20,000 years ago, that was the end of this last cold period. And then we warmed up out of this cold period into the Holocene, that 10,000 years of sweet climate. And now what we're doing is we're looking at putting carbon dioxide up to levels that haven't been seen for hundreds of thousands, or probably millions of years. So we're changing our composition, we're changing the composition of our atmosphere in a way. We've now pushed past the 400 parts per million mark, which is about right here. And we've done it in the last 100 years. So this is a major change in the composition of our atmosphere. Now, often people ask me, how do you know that? And we have all kinds of techniques. I like to talk a little bit about how we know the information we know, because I think it's important. If you drill down through the ice cores, if you drill down through glaciers, there are glaciers in the world still, for the moment, where the snow doesn't melt completely every year, and it stacks on top of each other. And you can see these annual layers. And if you drill down through these annual layers, you can find tiny little bubbles where the air has been captured. And you can measure the old atmosphere all the way back hundreds of thousands of years. And that's how we build these records of carbon dioxide. And you can actually measure temperature separately. So you can measure both carbon dioxide and temperature based on the isotopes that get taken up and the amount of actual CO2 trapped in the little bubbles. So we have a pretty good record. Often people say, well, there was nobody around a million years ago. How do you know CO2 was what it was? Well, this is how we know. We dig it up. Now, every global warming talk has a slide like this, and this is mine. This is just a simple schematic of what causes global warming. So all of the important energy that we get for our planet's climate comes from the sun. And this energy essentially goes right through the atmosphere. You can see the sunlight when you walk outside, and even though it's gone all the way through the atmosphere. And the reason is because the sunlight is basically, the atmosphere is transparent when it comes to sunlight. Sunlight goes right through. Now, some bounces off clouds and other things, yes. But by and large, most of the energy goes right through the atmosphere, and it gets absorbed at the surface. And remember, 2/3 of the ocean, 2/3 of the surface is, I gave it away, ocean, right? So by and large, this energy is heating up the oceans. And that warm ocean radiates energy back out towards space. So we've got the energy coming in, gets sucked up by the ocean, and it gets spit back out toward the atmosphere. Now the problem is that the energy going out is different. It's long wave radiation, what we call infrared radiation. And the atmosphere actually absorbs that. And the amount that it absorbs it depends on how much carbon dioxide there is. So very simply, if we change the composition of the atmosphere, we're trapping extra heat on the planet, right? So the question is, where does the heat go? Well, Mark ruined the answer already by telling you in the beginning, but anybody want to guess? The oceans, yes. I heard somebody say it. That counts. You get extra credit. Yeah, over 90% of the heat trapped by global warming is going into the oceans. So if you're not really looking in the oceans, you're not really seeing the signal. So even though we think of global warming as global temperature increase, really it's here. It's global heating. It's that extra heat that's trapped in the ocean that's really important, that's really changing our climate. So almost all of the action in terms of global warming is really in the oceans. Now, why is that? Now, you can do a simple experiment. If you take a simple balloon and you fill it with air and you hold a lighter to it, what happens? It pops, yes. Someone on the internet said it pops. If you take a balloon filled with water and you do the same trick, what happens? It doesn't pop. That's right. Somebody said it. In fact, the water is so good at sucking up the heat that the skin on the balloon, the rubber, doesn't have time to melt. So this is an experiment you can try at home, or it's an experiment you can try in about a room full with 100 people. So, since I'm in a room filled with 100 people, I figured I'll try it. So some of you in the front row, maybe in harm's way. Trust me, I'm a scientist. All right, so this is a balloon that's about to be filled with air. And I could keep going and fill it with air some more. You guys want me to keep going? And if I tie it off, which I'm going to make a big production of. No, I'm not. I'm just going to hold the flame to it. If I tie it off and hold the flame to it, you guys can guess that it's going to pop. So let's see how long it takes to pop the balloon filled with air with a lighter. Are you guys ready? Are you sure you're ready? All right, here we go. You should close your eyes and your ears, and anyone with a pacemaker or heart condition, now would be the time to leave the room. Okay, here we go. Boom! Yes, it pops. So there's only one thing left to do, and that's try it with a water balloon. So we're going to do that. The water balloon won't pop either, just like in the video. And I know this because I'm a scientist and I've done this many times. All right? You people in the front row are in almost no danger of getting wet. This is strictly the policy of the auditorium that I use this bucket because there's all kinds of sensitive electronic equipment. You guys are fine. It'll be great. Because it's Valentine's Day, I decided it should be a pink ocean today. So we're going to try this. Okay. We're going to try this and just see what happens. And what I want you guys to do is count how long it takes for me to pop the balloon, okay? Filled with water. You're going to be fine. This almost always works. Here we go. You ready? Getting kind of nervous, guys. You guys are good at counting. Whew. It's getting hot in here. 20's good, right? Yay, we can stop at 20. Look. And actually, if you want to feel it, it's not even hot, right? Yeah, it's because the balloon is so good at taking up heat and the water sucks up all the heat, and that's why it works. Yay! It's science! All right. So, that was the scariest part for me. I know it was for you too. That's why I got to drink some water. So, what did we learn? Nothing. I knew it. Great. Really, the point here is that water is kind of an amazing substance, and 2/3 of our planet is covered by it to a depth of about 4 kilometers, a couple of miles. So this is a huge volume of water, and essentially what we're doing with climate change is holding a great big lighter to it and waiting for sea level rise to pop our balloon. On that happy note, just to kind of revisit what's going on, if we imagine our sun again and our atmosphere, before climate change started, so say during that 10,000 year period of climate happiness, essentially we were getting the same amount of energy coming in from the sun as was going back out into space. And what happened in the last 150 years is we reshaped the atmosphere. We changed the composition of the atmosphere, and we started keeping more of this heat on the planet. So if you look at our little happy Earth, what's happening is he's getting warmer, right? He's turning into hot Earth. Now, eventually, this heat goes somewhere. It warms up the oceans. It warms up the atmosphere. Eventually, you get a warm enough atmosphere that it starts sending more radiation back out into space. So you achieve a new balance, a new Earth, a new climate. But the penalty for that new balance is that now you've got a warmer Earth. You've heated up your planet. But remember, I said that global warming is all happening in the oceans. So in order to get from the left Earth that's normal and cool to the right Earth that's hot and sweaty, you have to first heat up the oceans. And heating up the oceans is a huge task because they're so big. In fact, it takes something like 1,000 years for the heat we put in the ocean today to spread through the entire oceans and eventually circulate back up to the surface. So we're setting in motion changes by changing this composition of the atmosphere that are going to be with us for something like 1,000 years. So if you go back to my title about irreversibility, no way back, in terms of a human scale, in terms of people alive today, our children, our grandchildren, our great-grandchildren, we're really looking at changes that we're not going to be able to undo in any easy way for thousands of years. Sea level rise will continue to happen even after we stop putting carbon dioxide in the atmosphere because it takes the oceans so long to absorb and eventually redistribute this heat. So, is global warming really happening? I say yes. My friends say yes. If you haven't seen Ice Age 2, global warming is like the bad guy and sea level rise is happening. It's a great movie anyway. But not everybody believes that global warming is real. Some of our friends on the radio still don't agree. And in fact, also since Valentine's Day is coming up, I thought I'd just take a second and tell this little story. A couple years ago, I wrote a paper about climate change, suggesting that the oceans had actually cooled off a little bit. And Rush Limbaugh actually mentioned it on his show. He had this fantastic quote. He said, this paper by Josh Willis and John Lyman and these other guys is totally crazy. They have no idea what's happening in the climate. It doesn't make any sense. And he said, to overturn the world economy based on the musings of a few idiot leftist scientists is just stupid. And that's what global warming is actually all about. Thank you, Rush. And so it was, some of my colleagues that wrote the paper with me were, of course, horrified that Rush Limbaugh had talked about us on the radio. It turned out that I kept looking at this data and this signal of ocean cooling, which actually, in a sense, really didn't even make sense to me. And I dug a little further, and it was February of, I think, 2008, I want to say. And I was standing with my wife in the kitchen, and I was looking over a talk about ocean cooling that I was supposed to give at a big climate center in Colorado the following weekend. And I found this result, and I thought it was really surprising. Some of the data that was going into it looked like it had been flawed, like it was too cold. And I wrote a friend of mine an email, and he wrote back kind of quickly and said, yeah, something's definitely wrong with that data. And I turned to my wife. It was actually Valentine's Day, and we were getting ready to go out for a nice dinner, and I said, I think I'm wrong about ocean cooling. And she said, okay, let's go get dinner. But dinner was kind of ruined because I was really worried. I had to give a talk literally the next day at a big climate center, and so I was just worrying the whole time, and dinner was completely ruined. As a reminder, my wife actually had a small business card made for me, which has my job title listed as Idiot Leftist Scientist. So if anybody wants one, you can see me after the show. But I think this is an important lesson in how science works because, we don't get the answer right the first time every time. But we keep hacking away at it. And so, eventually I wrote another paper and said, okay, I was wrong about ocean cooling, and Rush was right. I am a big, fat idiot. But one thing I think that we are quite certain about, and stands on a whole lot more research and papers than just my one bad one that Rush mocked me for, is the rise of sea levels over time. I mentioned a little while ago that temperatures went up and down with the cycles of the ice ages, and CO2 followed those as well. And sea level actually also went up and down with the ice ages because as you build a gigantic ice sheet over North America, the water has to come from somewhere, and it comes from the oceans. So during that period, 20,000 years ago, the oceans were 120 meters lower than they were today. So this is when you had things like a land bridge across the Bering Strait, and North America and Siberia were essentially connected. And so as we warmed up out of that period, sea levels began to rise and those ice sheets began to melt. And we had incredibly fast sea level rise about 10,000 years ago. And then it really started to level out. And if you look at just the last couple thousand years, we have a very new, very exciting record of this, incredibly accurate from, of all places, North Carolina. And in North Carolina, the land itself is sinking a little bit. And as it does, the ocean crawls up these salt marshes. The sea level crawls up these salt marshes. And it leaves behind a record because they're little critters that like to live in very specific levels in the tidal range. And you can dig a core in these salt marshes, or a number of cores, and you can reconstruct sea level back 2,000 years. And when you do that, and you account for the local land motion, what you see is that we essentially had 2,000 years, or at least 1,000 years, of very stable sea level. Sea levels were not changing hardly at all. Then, during what was called the medieval warm period, we had a little bit of rise right through here. And during what was called the Little Ice Age, we had maybe a little bit of decline. But what's really striking about this picture, what's really the amazing part, the last 150 years, where sea level's rising at 2 millimeters per year, in agreement with local tide gauges, by the way. These data have been verified by nearby actual instruments. And incredibly, this rate of sea level rise is different than anything we've seen in the last 2,000 years. So, remember, we've been through these ice ages, little ice ages and little warm periods, cycles of the sun coming and going and tilt of the Earth's axis and so forth, but nothing until the Industrial Revolution, until the rise of CO2 put there in the atmosphere by people, can really explain the warming and the incredible rate of sea level rise we've seen in the last 100 years. So to me, this is really the nail in the coffin in terms of the denier's argument that global warming is not happening or that it's not caused by people. Because you can't really explain this rise in the last 100 years without it. So I like to drone on about this, but I'll move on and look at just the last 100 years. And this is the period where we kind of have enough actual tide gauges in different places in the planet to get a good sense of how sea levels have changed in the last 150 years, 130 years. And if you look, they haven't increased at a stable rate. In fact, if you look at the first 50 years, they were going up at about 1 millimeter per year. In the second 50 years, about 2. In the last 20 years, about 3. So there's actually been an acceleration in the last 100 years. And even more recent research than this suggests that that acceleration might even be a little bit bigger than what we show here, because the early part might have been overestimated. We see a little less sea level rise in that first 50 years than is shown here. So this seems small. It's only about 20 centimeters, about 8 inches. And when you're standing on the beach watching the waves crash in, that seems like a small number, but remember, 2/3 of the planet's surface, right? So this is a huge area, and this turns out to be an enormous volume, 16,000 cubic miles of extra ocean in the last 130 years. So finally we get to kind of the more recent stuff, the altimeter period, the period where satellites really dominate our record of sea level rise. And we look in the last 20 years, my PhD was somewhere in here, and Rush was making fun of me somewhere in here. And finally, we're out here. But what's striking about this, and if you think back to my earlier discussion about the hiatus, where's the hiatus? In a sense, this is the global warming curve. And there's really no hiatus in it anywhere to be found. A few small bumps and wiggles, but nothing like what you see in the temperature record. But if you're not convinced by satellite data of sea level rise, you can look at satellite data of the Arctic. This is the minimum amount of sea ice we had in 1979, the first year we had a satellite to really look at the top of the planet. And this is the minimum in 2008. And so you go back and forth and you see really it's an incredible wastage of floating ice at the top of the planet. And I didn't just cherry pick 2 years. If you plot the time series, it looks like this. So we've lost about half of the area of the ice that's floating on the Arctic Ocean. And in fact, actually, that ice is thinned by about a factor of 2. So if you're thinking about the volume of ice floating in the Arctic, it's decreased by a factor of 4 in the last 20 or 30 years. So it's a pretty major change. But nothing says global warming like a polar bear, right? So in 2007, we had this major minimum, and the ice was being blown north, away from Canada. And the polar bears are hunters. They use the ice to try and catch seals, which are better swimmers than they are. But the ice gives them a kind of tactical advantage. So polar bears were literally starving to death because they couldn't find enough ice to hunt seals with. Now, I'm not a biologist, but my guess is the polar bears will survive global warming because they can always just move south and eat Canadians. But at the same time, this is a reminder that some of really the world's top-level predators, besides people, are beginning to feel the pressure of our changing climate. And so they do serve as an important reminder, kind of an iconic one, I think. But of course, you don't have to take the polar bear's word. We have another satellite called GRACE. This is a fun satellite because it literally weighs the continents. One satellite flies ahead of the other, and whenever it goes over something heavy, the pull of gravity literally causes it to speed up. Then when the second one follows, it eventually catches up, and by measuring the distance between the two satellites, you can actually infer the weight of the thing you're flying over. So if you're flying over something like Greenland, you can chart its ice loss over time. And this is a little bit older slide, but it's continued through the present period. And Greenland's been on Jenny Craig. It's lost a couple trillion tons already. So go Jenny. Anyway, the point here is that we're really seeing these huge changes in the ice sheets that are unlike anything that's been happening in the last several thousand years. If this had been going on in Greenland for 2,000 or 3,000 years, sea levels would be many feet higher than they are today. It's interesting, too, because Greenland's kind of melting in an interesting way. It starts with the most melting, the most ice loss in the southeast sector. But actually, there's also ice loss further to the north up on the western coast. And if you start asking, why is that, you immediately start, well, I'll come back to this in a little bit, you immediately start looking toward the oceans. It turns out the oceans are kind of eating away at the edges of the glaciers here and causing the ice loss to accelerate. But again, a picture is worth 1,000 words, and a picture of a glacier is worth at least a couple of satellites, I think. And this is a picture of a glacier in Alaska. Now, some of the glaciers were in retreat before global warming started in Alaska, but not like they are today. And the fact is that over 90% of all the glaciers everywhere in the world today are retreating. So this is a global signal that we're seeing all over the place. But this glacier's retreated miles. This was a picture in 1941. This was 2004. Many of the glaciers there are in retreat in really quite a spectacular fashion. But one of my favorite pieces of evidence for human-caused climate change was the breakup of the Larsen B ice shelf in 2002. And this was interesting. This was a couple of images captured again by NASA satellites. And in January, which is summer in the southern hemisphere, this is the continent of Antarctica is below here, and this is part of the big peninsula that sticks up into the oceans. And this region of this ice shelf is essentially a giant floating pillow of ice that lays out over the surface of the ocean that comes from the flow of glaciers which cut down through the mountains and then spread out over the water. So this is a piece of floating ice. And in January 2002, they saw these puddles appear. These are little dark spots where the sunlight's being taken up instead of getting reflected back out into space. And then in March, when they flew back over and took another picture, this entire shelf had broken up and collapsed. So all this fuzzy stuff are little icebergs, which are what is left of this enormous ice shelf. Now, what's interesting to me is not so much that a giant ice shelf broke up, but oceanographers went back and they drilled sediment cores where the ice shelf had been, and they found that the ice shelf had been there for 10,000 years old. So through the Little Ice Age and the medieval warm period and all these things that we think of, all the way back to when there was way more ice in the world than there is today. So these ice shelves go way, way back. They're the only thing older than Hugh Hefner to break up in the last 100 years. I really need a rim shot. Anybody got one of those? Anyway, so, but the Larsen B ice shelf, I think, is another really striking piece of evidence that something's happening today in this 100 years that really hasn't been happening for the last several thousand, and that's us. You know, if you ask where's global warming and you still think you can't see it, I think then you're really just not looking for it. So I want to come back really quick to Greenland with just the last couple of minutes here and talk about the ice loss there. I'm going to skip ahead. Oops. Mark mentioned my new mission coming up, which is called OMG, Oceans Melting Greenland. And that was the best OMG picture I found in all the internet. So if you have a better one, please send it to me. See me after the talk. But I want to talk just for a second about this because I talked a lot about sea level rise. But what's really amazing is the cause of sea level rise. So if you look at Greenland, and I talked about how the southeastern quadrant and the northwestern quadrant are both warming, or losing ice, what's interesting is that this is the place where the oceans are warming the fastest. And so when we started to look, when researchers started to go up close to these ice shelves or glaciers, the glaciers here literally run right off of the continent and into the ocean. So they're literally sticking right into the water. And that means ocean water can come right up to the face and melt away the face. And as they do that, then the glacier itself is free to speed up and dump more ice into the ocean more quickly. And that's what causes the sea level rise and the acceleration. So we proposed this a couple years ago to do an aircraft mission to essentially fly around Greenland and drop little sensors that would measure the ocean temperatures. And you can't just measure the ocean temperature at the surface, because it turns out that the oceans here have a cold, fresh layer that caps this warm, salty layer, which is climbing up into the fjords and into these trenches to eat away at the glaciers. So we designed an aircraft mission to drop little sensors and measure these things directly in the ocean. Another aircraft mission to fly over the ice and measure it with a radar. And over the next 5 years, we're hoping to literally kind of shower Greenland with observations, new observations of how the ocean's changing in the region right up close to the land, and also to fly over all the places where we know glaciers are literally sitting right into the water and feeling the impact of these currents, and try to answer the question, how much of the ice loss here is really because of the oceans, and how much are the oceans really threatening the ice sheet in the future? So we're really excited about OMG, and hopefully in a year or so, I'll come back and give you a talk all about this one and say all kinds of crazy stuff about Greenland. But in the meantime, I'll stop and answer questions. So we're going to do a little question and answer session here. So if you have a question, please come up to the microphone and ask me through the microphone so that everybody can hear, even people on the internets. And I think we may also get some questions from online if we have any. So please, thanks.
How long is Florida going to be by the time Florida sinks into the ocean?
When do we finally get rid of Florida? Is that what you're asking? Yeah, that's a great question. Well, Florida's already beginning to feel the impact of sea level rise. They've had about that same 8 inches that we've had pretty much everywhere else in the world. And they're beginning to have to protect areas that they want to keep and decide which areas they want to lose. But in the next 100 years, we face somewhere between 1 foot, which is probably unlikely, and 6 feet of sea level rise. If it's 6 feet, then really a whole lot of Florida is going to be underwater. And it doesn't happen sort of all, like one day you walk out and your backyard is flooded. It's that storm that didn't used to get you, now it gets you. It's that high tide that didn't used to get you. Now it gets you. And so it's kind of this creeping thing, and one that people are going to have to decide what kind of stuff they want to protect and what kind of stuff they want to let the oceans reclaim. So, Florida is going to face some tough decisions in the next 100 years. Now, is it all going to be underwater by the end of the 21st century? No. But major cities along the coast of Florida will face trouble from sea level rise. The question is how much. And part of it is we don't know the answer entirely. We have some idea, like I said, between 1 foot and 6 feet. But these things like the oceans eating away the glaciers, there's a whole lot that we really don't understand about that. So our ability to say 1 foot or 6 feet is limited at this point. And in a way, that's a bigger risk than if we already knew. If I could tell you it's definitely going to be 2.5 feet by the middle of the century, then you could say, okay, well, it's time to abandon this city and move on. But because there's this uncertainty, in a way, we face bigger risk because we might choose to ignore it, and then you really have troubles.
Well, I used to be stationed on Kwajalein in the Pacific, and just a foot rise would sink that entire island, and a lot of islands in the Pacific. Now, my question is, how do we stop global warming since it's all our fault? Do we ruin our economy? Do we stop putting we got to watch the way our light bulbs, what we use, what kind of cars we drive, our whole life becomes all screwed up? Or what is the major cause of global warming besides me and us individuals that are being hounded by the left?
Yeah. Well, some applause there. I think the fact is that we're going to pay the cost of global warming whether it's today or tomorrow, and human activity is definitely the cause of modern-day sea level rise. It's the burning of fossil fuels, but that's not to say that it's hopeless. I think there's plenty of opportunity to innovate new forms of energy and to wean ourselves off of our addiction to oil. And if we do, then I think we can stave off some of the biggest consequences. But if we don't, we'll eventually pay for them one way or another.
Well, the way it looks to me like it's just global pollution. Basically.
Yeah, pollution's a big problem.
And we don't do nothing with China or India. They just going wild with it. And we're the one in America that get always told that we're the bad guys.
Well, of course, there's plenty of blame to go around. But China and India are trying to innovate solutions just like we are. In fact, China's better at building solar panels than we are. So, we got to pick up the pace a little bit.
Yeah. Well, thank you.
Thanks for your question.
Hello. Is Jason-3 equipped with a microwave and a radiometer?
There is a radiometer on board Jason-3 that will measure how much water the signal has to travel through when it travels down through the atmosphere. If it goes through water and clouds, then it changes the travel time a little bit. So the radiometer essentially measures that separately so that you can correct for it. But yes, it does have a radiometer in addition to the actual radar instrument itself, which is measuring the travel time and telling us the height.
When is the launch going to occur?
Well, right now, the launch has slipped past its original March 31st date. We don't yet have a firm date for a new launch, but we're looking at the summer, maybe July, sometime around there. But we haven't been given a firm launch date yet, so they're still looking at issues with the trying to qualify the SpaceX rocket, which is going to be our ride to space. NASA makes you jump through a bunch of hoops before they'll put one of their babies on your rocket. And but we are excited that a lot of the waiting is hopefully behind us, and we're hopeful that it'll be this summer, we really got our fingers crossed.
Oftentimes, launches are delayed due to high winds or something, like the launch of the Discover. Every day it's supposed to be launched, and then the window opens and closes and whatever. And yet, it's so inept because it's dependent upon, like, data from SOHO with the actual measurements that can be passed on to Dragon and Discover.
Right. Well, you know, we want the good weather and a good window so that we can hit the right target, right? You know, we've had a couple of successful launches out of Vandenberg on previous missions, and you know, we're really excited. So we're optimistic and looking forward to a launch this summer. So keep your fingers crossed for us.
I certainly will. Thank you.
Thank you.
Hi, my name's Ben. I'm from Redmond, Washington. And I'm a huge fan of the Earth observation satellite program, so don't take this as criticism, but what is the advantage to having multiple Jason missions active at the same time? Is it just that the new ones have better or newer instruments?
Oh, that's a great question. There's a couple reasons you want them to operate at the same time. One is so that you have this unbroken record. You know, all of our missions so far, TOPEX, Jason-1, Jason-1, Jason-2, have had some overlap. And that overlap has really allowed us to get an unbroken record of sea level rise for 20 years. So part of the reason we want to fly them both at the same time is so we can make sure we really understand the new instrument before we turn over the main mission to it. But there's other reasons to fly them both at the same time too. If you move one over into a slightly adjacent orbit, which is what we did between Jason-1 and Jason-2, then you can essentially double the resolution you get. These missions look straight down, and they give you a single point, and they fly in a pattern to kind of cover the whole Earth in 10 days. But if you have two of them, you can essentially double your resolution, and you can see smaller scale stuff in the ocean, things like the eddies that push the oil slick around in the Gulf of Mexico during the Deepwater Oil Horizon catastrophe. Those things are smaller, and the more satellites you have looking, the finer the resolution of things you can see. A final reason, which is something we did with Jason-1, is eventually we might repurpose the mission, and instead of trying to do oceanography, really try and look at marine gravity. So it turns out that little mountains and troughs and ridges on the bottom of the ocean actually bend the shape of the sea surface also from the pull of gravity. Now, this is something they don't move around. The mountains stay pretty still. So if you subtract out the time average signal, you can really look at the oceanography. But if you look at the actual complete signal, then those little bumps and wiggles tell you where the seamounts are. They tell you where the underwater mountains are. So what we actually did with Jason-1 was move it into a slightly different orbit where it didn't really repeat. And it measured a small swath that traced along the equator and covered the entire oceans in a much finer mesh. And that's how they began to really improve the knowledge of the shape of the sea floor. So we might do something like that with Jason-2 in a couple of years as it starts to age and becomes more likely to eventually kick the bucket.
Your response just partly answered my question, but I was curious, what kind of techniques do you use to validate the accuracy of your measurements? For example, you mentioned about that Valentine's Day episode where you realized, I don't know if it was by intuition, that you understood the data wrong. Like, what was the thought process going into that?
Oh yeah, what's keeping Rush off my back with the satellites? Yeah, that's a great question. Well, we have a lot of ways to, we have a lot of other things to compare our satellite mission with. So we have tide gauges that are spread all across the planet on coasts everywhere that measure how the sea level changes, and we compare those with how the satellite's telling us it changes. We also have a few dedicated places that the satellite flies directly over. There's one right off the coast of Santa Barbara called the Harvest Oil Platform. It's just off the coast, and it's had a continuous sea level measurement right there on the platform. And our satellite flies right over it, so we get a direct look, and we can compare directly and see just how good the satellite is doing. So we also have a whole other suite of satellites and an entire team of about 200 people who every year, all the time, are just looking at this data, trying to make sure that it's accurate and agrees with other things we're measuring that are consistent. What happened to me on my PhD was a different story, and that was actually a symptom of changing to a new kind of data. We had been measuring the temperatures of the ocean with small probes for decades, and we switched over to a new system, and there were some differences. That was part of the problem, and then part of the problem was that some of the new floats just weren't, some of the new instruments just weren't working right. But what eventually allowed us to tease out the difference between the new and old data was actually satellites like Jason. Because as the bad data accumulated and you got enough of it, you could begin to look at the difference between what the satellite was telling us and what the floats were telling us. So it's really an ongoing, it's always a work in progress. We're always double checking the data. We're always looking back at the results, trying to make sure that we're getting it really right. And science is it's not a one big discovery after another kind of thing. It's a kind of a 3 steps forward, 2 steps back process. And that's really part of what makes it so accurate in the long run, is that we're always checking ourselves. But, you're still left with those occasional moments where Rush Limbaugh's making fun of you, so.
I think you said the precision of the radar altimeter is about 1 inch.
That's right.
Yeah, so for a sea level rise of a few millimeters per year, obviously that's not particularly precise. So
Yeah,
how do you actually tease it out? Do you just take lots of measurements and statistically
Yeah, that's
figure it out
exactly
that
it.
way?
That's a great question. It's really good. What do you tell you? That was a great question?
No, that's right.
That's my man. Yeah, okay. All right.
And
Yeah,
you said
that's right.
you also measure something else, this tilt or something? What was
Yeah,
the other thing?
so essentially if I measure the height over here
Yeah, okay.
and the height over here, and they go like this, then the reason they went like this is probably because there was a current, an ocean current at the surface. So literally when the water's moving, it feels the rotation of the Earth, and it winds up causing a tilt in the surface of the ocean. So originally, these satellites were designed just to measure that tilt. We weren't thinking about global warming. The guy sitting next to you, by the way, is one of the guys who made this first mission, Topex Poseidon, happen. So any questions that, yeah, there he goes. Bill can answer. But essentially, it was designed to measure that tilt. We were really looking for the currents. But it turned out that it was so accurate, and by averaging over the whole globe and really looking at the kind of biggest scales, you get millions and millions of measurements every 10 days. And you average them all together, and you average a bunch of 10-day periods together, and you can really see this long-term change.
It's like looking for an exoplanet, just that little bulge in the star motion. Yeah,
That's
thanks.
right.
Good
Yeah.
talk. Yeah,
Thanks.
My question's about the Pacific Decadal Oscillation. And my impression is that we don't really understand it very well. And so my question is, to what extent Jason data and maybe data from probes that float up and down in the ocean, to what extent do we think that oscillation is chaotic and really can't be predicted, or what extent do you think you'll be able to understand it better? So, because my impression is we've only sort of seen one cycle, right? 20 years or so. We don't have any way of knowing what it was on previous cycles.
Yeah, it's a great question. Just like you said, the Pacific Decadal Oscillation is something that's decadal. It takes a decade or two to change from one sign to another, one phase to another. And we've only had our satellite for 2 decades. So we don't have an especially long look at the Pacific Decadal Oscillation. But what's interesting is that over those last 2 decades, it's really changed a lot. It's changed a lot from a very positive phase, which is associated here in California with more rain, to a very negative phase, which is associated with more drought here in California. And it's interesting that there are these weather connections, because those actually allow you to trace back over time things like the Pacific Decadal Oscillation by looking at the growth of trees from tree rings and other proxies. So our satellites only go back 20 years, but we have a few other data sets. Surface temperature goes back maybe 40, 50 years. Some surface pressure measurements maybe go back farther than that. And when you get into longer time series, you're really looking at these tree rings and proxies for the Pacific decadal oscillation. But you're right in that our ability to really tease all that apart, we've only got about 10 or 20 years worth of data. So we really do have a lot to learn about the Pacific decadal oscillation. But at the very least, we can say that it kind of goes back and forth between a certain range, and that at least over the last, say, 50 years, it probably takes somewhere between 5 and 20 years to change. So we have some sense that it's kind of these decades-long timescales. But you're right. The real underlying cause probably has something to do with the ocean, probably has something to do with the way it interacts back and forth with the atmosphere. But what's really driving this oscillation, I think, is still unknown.
Thank you.
Oh, we have questions from people out in interspace. Great. So how long do you want me to drone on up here, Mark? As long as it takes to answer all of these. Okay, so I'll just, if you have other questions, feel free to go ahead and line up at the mic, but I'll just go through a couple of these really quick because I think they'll be fun. So Elijah Michael asks, how long will Jason-3 be active? We hope longer than Rush Limbaugh. But we build these satellites to last between 3 and 5 years. So they have a must-live for 3-year kind of design, and we really hope they live for 5 years, and we kind of expect them to. But of course, its predecessors have done fantastic. Topex lasted 13 years. Jason lasted 11. Jason-1. Jason-2 is now, let's see, 2008. What year is it? It's getting up to 7 years old. So we're optimistic that it will outlast the 5-year life expectancy, and maybe it'll go 10 if we're lucky. But we can't really plan on longer than 5 years. Jeffrey B-Boy Lizard asks, are there other things besides CO2 affecting global warming? Well, Jeffrey B-Boy Lizard, CO2 is the big dog when it comes to causing global warming. There are other things that we do, like things that emit methane. There are other greenhouse gases. There are some other effects like reshaping the surface of the planet, turning the desert like we used to live in around here into parking lots and golf courses. These things all affect the climate, but in terms of the global climate, in terms of the whole planet's heating up, really CO2 is the major cause. It's definitely the biggest dog, and it's the one that lives the longest in the atmosphere. So CO2 has an expected lifetime in the atmosphere of hundreds, if not thousands of years. The ocean sucks up a little bit of it, but by and large, what we put there, we're stuck with for a long time. Oh, this last one's from Marvin the Martian. What effect would a large volcanic eruption or asteroid strike have on our climate? Well, Marvin, I know you want to blow up the Earth. An asteroid or a giant volcanic eruption could have a pretty major impact on the climate. In fact, it's been suggested that this was partly the cause for extinctions in the past. A big meteor would hit the planet and blow dust up into the stratosphere. And effectively, a volcano can do the same thing. It can put all this soot into the stratosphere, and this can actually cool off the planet, so you can get a little ice age or a little winter. In fact, we've seen this in the not too distant past. Mount Pinatubo was a major eruption in the early 1990s, interestingly, right at the launch of of Topex Poseidon. And it's been suggested that it cooled off the Earth just a little bit for a couple of years. So these kinds of things can have a big impact. But of course, soot eventually settles out of the atmosphere, and these things eventually kind of go back to the way they were. Whereas CO2 can really last hundreds, if not thousands of years, like I said. So Keep working at it, Marvin, but we're sending Bugs Bunny your way. All right, guys, thank you very much.